Hi, I'm Andrew Connell, and I'm a Microsoft MVP in the area of Microsoft 365 development. And I have a lot of experience with SharePoint development, including all of the different development models that we've had, Microsoft Graph development, Microsoft Teams development, and developing add-ins for Microsoft Office, as well as working with Microsoft Identity, including Azure AD. Microsoft Graph has built-in throttling to protect its resources from being overloaded and unable to respond to requests. So when building applications that use Microsoft Graph, you want to ensure that the application can react to throttling events. In addition, you should consider implementing throttling strategies to avoid throttling altogether. In this module, we're going to look at how we can optimize network traffic with the Microsoft Graph by understanding throttling. We're going to focus on understanding throttling in the Microsoft Graph, what happens when requests are throttled, how do we identify throttling requests, and then explain some common throttling scenarios. Microsoft's Office 365 developer vision focuses on the user's experience and their data. As a developer, you can bring your applications into their user experience. With over 1.2 billion users of Office worldwide, this is a huge opportunity to provide a window into your applications, as well as being able to connect into their data and add intelligence to your applications. There are currently 850 million events created a month and a total of 470 petabytes of data or more in the service that can add value for your users. Microsoft Graph is the gateway to your data in the Microsoft Cloud, as you can see from the list of resources, services, and entities on this slide. There are lots of things that you can take advantage of in the Office 365 platform. You can work with mail, calendar, contacts, tasks, in addition to content inside of SharePoint sites and lists, files inside of OneDrive, and interact with Microsoft Teams and many more things that you can take advantage of. Each of these services typically has its own API that you can leverage to read and write to these different services. However, it can be challenging and cumbersome to work with these different services, as each has implemented their own endpoint, permission model, and syntax for performing some operations like searching and other subtleties. Each endpoint is also secured with Azure AD, which means that developers will need to authenticate with Azure AD and obtain an OAuth access token for each service they want to work with. The Microsoft Graph addresses many of these challenges by acting as a proxy to a lot of the different services. It encompasses data residing in Office 365, such as mail, calendar, and contacts, and OneDrive, as well as many others. In addition, it also provides access to Windows 10 and enterprise mobility and security under a single endpoint. This endpoint, https://graph.microsoft.com, allows developers to create applications that will only have to authenticate once and obtain a single access token that can be used to retrieve data from multiple sources, greatly simplifying the development process. Each service will still have their individual permissions or scopes, but all of these permissions are defined in a single place under the Microsoft Graph endpoint and handles the underlying calls and permission requests to each of these different endpoints. As the previous slide stated, the Microsoft Graph is your gateway to all data in Microsoft 365. It is a single resource that proxies multiple Microsoft services. Because the Microsoft Graph acts as a proxy endpoint to multiple endpoints for each Microsoft 365 service, it will simplify the process of obtaining OAuth access tokens that you must include with each request to one of these endpoints. Unlike the process of obtaining a different token for each endpoint, the Microsoft Graph enables you to obtain a single access token to submit requests that can retrieve data from all the services and endpoints that the Microsoft Graph exposes. One of the challenges we used to have to deal with these different services was determining the endpoint URL for each service, as some of them were unique to each user. To address this, Microsoft created a directory service that you could query to determine what the URL was for the different services for a particular user. However, the Microsoft Graph greatly simplified this with two special endpoints, the /me and the /myorganization endpoints. These will take you to the root of your user entity or your organization within the Microsoft Graph. This module will explain how you can easily find relationships between entities in the Microsoft Graph and traverse these objects to find related content. Using the /me and the /myOrganization endpoints in combination with the ability to traverse related entities, the Microsoft Graph makes it easy to access your data. Developers can create all sorts of applications that will communicate with the Microsoft Graph. And to support as many developers and as many platforms as possible, the Microsoft Graph has two options for developers to choose from when integrating the Microsoft Graph into their applications. At its core, Microsoft Graph is a REST API. This means that developers can use any platform, any framework, and any programming language they are most comfortable with. The only requirement is that they issue a common HTTP request and process HTTP responses, which pretty much all relevant platforms and frameworks and languages can do these days. In addition, Microsoft Graph also provides native SDKs for developers who want to leverage a rich programming model with their applications. These SDKs are available for multiple platforms and simplify the process of interacting with the Microsoft Graph REST API, abstracting away the tasks of constructing, submitting, and processing the REST requests and responses with Microsoft Graph APIs. You will likely find an existing SDK for the platform and language that you are working on, as you'll find almost all of the popular platforms are covered, including .NET, iOS, Android, Java, PHP, Ruby, JavaScript, and many, many more. Microsoft Graph supports two styles of authentication. One supports the users to authenticate using either Azure AD accounts, which are also known as work and school accounts, or a Microsoft account. The former account is typically used to access content and resources within other Office 365 services and Microsoft 365. The latter account type, a Microsoft account, is used to access consumer services such as OneDrive Consumer, Outlook.com, and other related services. Now, what's nice about Microsoft Graph supporting both styles of authentication is that the same API and the same endpoints can be used to create applications that will expose business data to Microsoft in Microsoft 365 or consumer data within the Microsoft Consumer Services. This makes it easy for developers to learn a single API and have the ability to configure their application to support both businesses and consumer data that is driven strictly by the user and what type of account they're going to log in with. Microsoft Graph is designed to handle a high volume of requests. If an overwhelming number of requests occur, throttling helps to maintain optimal performance and reliability of the Microsoft Graph service. Throttling limits the number of concurrent calls to a service to prevent overuse of resources. Throttling limits vary based on the scenario. For example, if you're performing a large volume of writes, the possibility for throttling is higher than if you are only performing reads. Developers may ask, what are the throttling limits per hour or per day? But this is not an easy question to answer. Microsoft Graph is a proxy service that provides access to multiple Microsoft-hosted resources and endpoints. And each of these services has their own process for calculating when requests should be throttled. In addition to the different services, not all the requests are treated equally. A read request is not as demanding on the services as a write operation is. For example, not all read and write operations can be treated equally. A read request for just the ID and the name of 50 groups is a very different request from including the expand query operator to include, in addition, the ID, name, and email address and phone number for all the members in those groups. So not all reads are treated equally, and not all reads and writes are treated equally. What does Microsoft Graph do when it determines that a request by a specific client should be throttled? Well, first let's consider what it means when a request is throttled. When a client issues a request that is throttled by Microsoft Graph, this is the service's way of telling the client, hey, your requests have been determined to be negatively impacting the service, which can impact the health and responsiveness and reliability of the service for everyone else, including you. So in that situation where requests are being throttled, Microsoft Graph is telling the client, look, don't issue any more requests for a certain amount of time. And this time frame is commonly just a few seconds, but some services may require a more lengthy delay. Any request before this delay time has elapsed will continue to be throttled by Microsoft Graph. And in some cases, it could also cause the delay to be extended. In some scenarios, while some requests are throttled, other requests by the same client to the same endpoint may be allowed. So, for example, A high volume of write requests could trigger Microsoft Graph to throttle future write requests, but read requests to the same endpoint would be allowed. The first step to understanding throttling is you've got to be able to identify when a request is throttled by Microsoft Graph. Now in HTTP APIs, the result of a request is indicated by the HTTP status code that's returned. The HTTP status codes are classified in groups. For example, successful status codes are in the range of 200 to 299, and common successful status codes include 200, are in the 200 class. That's used when requesting a resource. Or like 201s and 204s. Those are used when writing operations for creating and updating or deleting resources. Error status codes are in the ranges of 400 to 499 and also in the 500s. A common failed status code includes 400, that's a bad request, 401 and 403s, which usually mean there's a permission problem or an authentication issue, an authorization issue, and a 404, which means I can't even find what you're asking for. Now, the one we're interested here in this module is the status code that's returned for throttling requests, and that is 429, and that stands for too many requests. All requests that are throttled by Microsoft Graph will return a 429 when they're throttled. Now, another status code that you may receive is a 503. That means the service is unavailable. Now, Microsoft Graph returns the service unavailable code when the service is unhealthy and is not related to any throttling or traffic from a specific application or request. When this happens, well, there's nothing that you can really do. You can't do anything to avoid it, because if it happens, then that means that the graph is having a problem. But it is recommended that your application is built to handle this response code. But again, there's nothing that you can do to avoid this from happening or to delay to keep it from happening again on your application. Now keep in mind, Microsoft Graph is a proxy service to multiple endpoints and services, such as Azure Active Directory for users and groups, Exchange for calendar, contacts and messages, OneDrive and OneNote and SharePoint and Microsoft Teams, among many others. Each of these services have their own rules and calculations for when limits are exceeded and future requests will be throttled. Many, but not all, of these endpoints will also return an additional value in the response's HTTP headers that the requester can use to determine how long they should delay before resubmitting another request. This header value, called retry after, is typically an integer that represents the number of seconds the client should wait before submitting the request again. Any request sent prior to this time will continue to be throttled, and many may cause the retry after value to get increased as well. However, not all services include the retry after value, so your applications should have a default number to rely on when this header is not included. It's important to keep in mind that some services have a hard-coded retry after value as well, while other ones have a dynamic value that are calculated based on the type of the request and the current conditions. Therefore, you should not treat one retry after as a universal or a uniform number across all the services and for all future requests. Now that we've covered what throttling is and why requests could be throttled, and also what it means to be throttled, let's look at some of the common scenarios that can cause requests to be throttled. Now, this is not an exact science. You're not going to find reliable metrics that can be applied or assumed across all applications and endpoints and request types. Rather, you just need to consider what goes into dealing with requests that should be throttled. As a general rule, you can think of it like this. How expensive is my request on a particular endpoint is the real determining factor. The more expensive it is, the fewer of those requests that I can submit in a very short amount of time. Now, what is used to determine how expensive this request is? Well, that's the part that depends on the different situation. Which endpoint are you requesting? Is the request a read operation or is it a write operation? What kind of data are you looking for, and how complex is the request? So here are a few examples that can experience throttle requests. If you issue a large number of requests across multiple endpoints in a tenant, or a large number of requests from a specific application across multiple tenants, you might get throttled. If you submit a large number of requests for a large data response, so consider a request that uses the expand query operator and it tells Microsoft Graph to get additional data and include it in the request. If that request is not using data limiting query parameters such as $select or $top or $skip, for instance, the service has got to work a lot harder to retrieve and include a larger data set in the response. That would be a much more expensive request than asking for just the name, email, and ID of a user. Another scenario is a large number of complex requests. So similar to the last one I mentioned, consider a request that is forcing Microsoft Graph not to only retrieve additional data, such as the case when I'm using the $expand query operator, but also to perform some conditional checks on the data, such as using complex filter query parameters to limit the data results. As I previously stated, consider how expensive the request is. The more expensive it is, and the more these requests you send, the more likely it is that these requests will eventually be throttled. In this demo, we're going to look at working with a .NET Core console application to query the Microsoft Graph. Now, what we're going to do is this console application, the goal of it is to show you what throttling looks like. So we're going to try to get throttling to kick in into our application. Now, this can be kind of tricky sometimes to force throttling to happen, especially when you're working with it on your local laptop. But the demo here is made to be as simple as possible to show you this in action and to show throttling actually happen. A way that it's more common that you would see throttling kick in is when you are you're running an application at scale. So like if I had deployed this console application to Azure and had it run across multiple containers or multiple VMs, it has a better chance of being throttled. So what you'll see is it kind of get throttled a little bit, but it'll serve the purpose of what we're trying to do, which is we want to see throttling kick in, we want to see what the effects are, and we want to see how to get around it. Now, for this application to be able to work, the first thing we're going to have to do is we're going to have to create an Azure AD application that we're going to use, our console application is going to use to authenticate with Azure AD and to obtain an access token and to call the Microsoft Graph. So what I'm going to do is come over here to my Azure AD admin center, and I'm going to go create a brand new application. So I'll go to my app registrations and create a new application called my Graph Throttling Demo. And I'll leave it set to just a single endpoint. I'm going to click register. And we have our directory ID or the tenant ID and the application ID. We're going to come back and work with those a little bit later. We're going to grab those and update our application in a minute. But first, we need to go through and do some additional modifications to our Azure AD application. So I'm going to come over here to our certificates and secrets, or our authentication tab. And I'm going to go in, I want to modify this application. Now, this is going to be what's called a public client application, meaning that the user is going to log in this application using the username, password, resource owner grant flow. And so what I'm going to do is I need to specify a couple things. So it's a public client, so it's going to be a desktop client. And I'm going to say we're going to use this MSAL redirect, hardcode redirect URI. And then I'm also going to say that the client type, this is a public client. So I have to turn this on in order for this to be a public client, be able to use it this way. And again, this is only really applicable when you're doing things with, like, say, a public client where you would not provide an app secret, like in a mobile client or a desktop client. And that's what we're doing with our console app here. The next thing we need to do is need to grant it some permissions. And so I'm going to come over here to my API permissions, and we're going to grant it a permission of a delegated permission, actually, of mail.read. So I can grab mail.read and I'll say add the permission. Now, we're not going to go through the process of trying to deal with all the consent framework and prompts and everything with our application. So what I'm going to do is I'm just going to go ahead and I'm going to go ahead and automatically grant consent to all the users in my organization for this permission. So we don't have to worry about that. So let's go back over here to the overview of our app. And I need to go through and get these values and update our console app. So first we need our tenant ID. So I'll come over here to our application. And we have this app settings.json file in our app. So I'll just go through and modify these values with the IDs of this application. So we got our tenant ID and we need our application ID as well. Okay, so now let's take a look at the code here. So what is this application going to do? So what we're going to do is we want to see two things. I want to see this run first using the HTTP client, and then you'll see in later demos where we're going to be working with the graph client as well. So here what we're going to do is we're going to first prompt the user for their username and their password, and I'm going to use those to get an instance of an authenticated HTTP client. Now, we're not going to go through the details of how to get a client and authenticate it and do all of that stuff to call the Microsoft Graph, because we want to focus on just the throttling aspect here. I don't want to go through a very detailed, comprehensive piece on how all this works in terms of the how to talk to the Microsoft Graph or communicate with it. That's beyond the scope of what we're trying to cover here. So my next thing that we're going to do is, notice I'm just setting up a couple variables here. So what's going to happen is we are going to loop through and create 100 requests. And our requests are going to be asking for all of the email messages in the mailbox for the current user. So what I'm doing here is I'm creating a collection of tasks, and then I'm going through and I'm going to create a new task to go asynchronously grab all the messages for the current user. And when it succeeds, I'm going to write out just this dot that you see right here, that I'm actually making the request. If the request is good, then I get a response back of okay, then I just add that to my counter. Otherwise, I write out an X for every request that failed. All right. So that's just building an array of, or a list of 100 different requests that we're going to execute. Now, what I'm then going to do is I'm going to say, go ahead and start running all those requests and wait until they're all finished. So this line right here, these two lines right here are effectively saying, go submit all 100 of those requests as near to the exact same time as possible, instead of looping through like you saw up here. When that's finished, I'm going to write out, here's how many of the requests actually succeeded. And then it's going to write out, here's of the ones that failed, here's the failed one that we got back and the response headers. So let's see this in action. Let's see what happens with this. So I'm going to come over here to my console. So let's jump over to our console and let's run the app. I'll first build it. And then we're going to go ahead and run it. So I'll do .NET run. So I'll enter my username in, and then it's going to ask me for my password. Now, when this goes to run, this is going to take a second for it to get going and really see it run. And the reason why is because it's building up all of those 100 requests, and then it's going to submit all those requests at once. Those requests can take a couple seconds each time that they run, and that's just going to take, that could take like 30 or 40 seconds for it to run. So with the power of video editing, we're going to go ahead and jump ahead to when this is actually finished. Now you can see that the request is actually running. Some requests were succeeded, some of them failed. You can see only 34% of my requests actually succeeded. And the reason why? Well, the reason why they were only a few of them were succeeding is because many of them were coming back as being throttled. They were getting a 429 response, which is indicated by this too many requests response that was coming back. One thing that we may have seen, and in this case we did not get it back, was the presence of a retry after header. Now in this case we didn't get one back. Had we received one though, we would have it would have had a value in it of how many seconds that we needed to wait. So in this case here, we probably should have some sort of a fallback mechanism that we're going to talk about in a later section within this module on how we should deal with the case when we don't get that retry after. But in this demo, I just wanted to show you kind of what is the experience here of if you just fire all of your requests nonstop without any kind of consideration on if there's any throttling. And in this case, well, we issued 100 requests to the current user's mailbox, and we see that only 34% of those requests actually succeeded. The rest of them were throttled, and we didn't do anything with those throttled responses. We just let them fail. So now let's move on to the next section and talk about ways to how we can deal with it and have throttling strategies that we can deal with throttling. In this section, we're going to look at how we can implement different throttling strategies in our applications to avoid being throttled by Microsoft Graph. We're going to specifically look for options for addressing throttling, avoiding common throttling scenarios, and implementing throttling strategies. Now, if an application relies on an external service that implements some request throttling or rate limiting, the developers of the application should incorporate this in the application design. Now, there are two different approaches that you can consider when building an application that relies on Microsoft Graph to address throttling scenarios. First, consider avoiding scenarios where a request could be throttled. Avoiding the issue completely is always the best approach. However, the application should also assume that while the developers try to avoid throttling scenarios, it still may happen, and therefore, the application should address what happens in those cases. The application should always assume the request will be throttled, but developers should do what they can to avoid them from hitting throttling limits. Now, one way to avoid throttling is like exceptions or errors in your code. Developers always strive to avoid errors in your code, but they happen. There's a reason why try-catch-finally construct actually exists. While you should strive to avoid them, you should also incorporate logic in your code that accounts for when it does happen. Let's look at the first approach to addressing throttling strategies, avoiding the situations where requests are throttled. This is the best approach to try and avoid any scenarios where your application request to Microsoft Graph will be throttled. Now, to do this, you need to understand what causes requests to be throttled, and this was covered in more detail in the previous section. Fundamentally, requests are throttled when they put too much of a demand on the target service. This happens when a high volume of requests are received over a very short amount of time. However, there is no set number on how many requests can be submitted over this time. The reason is because not all requests are equal. A write operation is generally more expensive than a read operation, but a complex read operation that includes a lot of child collections using the $expand query parameter or a complex $filter query parameter may be much more expensive than a write operation. There are two strategies that you can implement in your applications to avoid requests from being throttled. First, limit the number of requests to Microsoft Graph over a short time period. Another option is to limit the number of operations per request. A query that includes multiple $expand and $filter query parameters is much more expensive than a simple read operation that limits the data set using the $select query parameter. However, keep in mind that these are not perfect strategies where you can ensure your application is never throttled. Your application could experience a burst in traffic and usage that makes it impossible to completely avoid some requests from being throttled. Avoiding scenarios where your application's requests to Microsoft Graph will be subjected to throttling, it's always the good first approach, but as I said earlier, your applications should incorporate logic for situations where requests are throttled. Now, the first step is to identify when the requests are throttled, and this can easily be done by inspecting the HTTP status code within the response. The status code 429 includes or indicates that too many requests are happening, and this is how Microsoft Graph tells the client that their requests are being throttled. In addition, how many responses include many responses include an HTTP header of retry after that specifies the number of seconds the client should wait prior to submitting another request. This includes repeating the same request or additional similar requests. However, consider that not all endpoints in Microsoft Graph include this retry after header value. In these cases, your application should have a default delay it uses. Also consider implementing an exponential backoff strategy for subsequent requests. Consider the situation where a response of 429 comes back with no retry header and you delay for 2 seconds. If your requests continue to be throttled, maybe the 2-second delay isn't long enough. If you replay the request, if the replayed request continues to be throttled, consider doubling it to the next request, and so on and so forth to improve the chances of a future request exceeding. The application should also have an upper limit of how long the exponential delay could be, and if exceeded, it should probably trigger an exception to notify your user what's going on. Now in this demo, we've taken the previous application that we created in the first demo, and I've made a bunch of changes to it, and I've done it in 2 different ways. So what I've done is I've implemented some throttle management strategies, and we've done this with 2 different options. The first way you see I've done it is I've created an instance of our application as just using the HTTP client, like you saw in the previous demo. The second option uses the Graph client, and you'll see what's nice about using the .NET SDK for the Graph client, for the Microsoft Graph, because it does a lot of stuff for you, makes your life a lot easier. Now, if you want to see how to go about building this application, there's a lab associated with the module that this screencast is tied to. Go refer to the lab to walk you through all those steps. In the demo here, we're just going to focus on the code that has already been built. So what I have here, again, we're using the same Azure AD application that we used in the previous demo. And what I have here is, if I come over here and look at this, at the program, let's walk through and let me explain what's going on here. Now, again, remember, we're not using the Graph SDK, .NET SDK. We're using just a raw HTTP client from the .NET Core. So what we're doing here is I am going to come over here and get a reference to the current user's username and password. And here what I'm going to do is I'm getting an instance of an authenticated HTTP client. And what that's doing is that's using the current configuration for the current app and the username and the password for the user to go authenticate and get an access token, and then use that access token to include it as an HTTP header in the request that we're going to submit to Microsoft Graph. So here what I'm doing is I'm defining what the response looks like. So in this case here, I'm saying, go get the ID of my message, of all the email addresses in my mailbox, get the ID property and give me the top 100 email addresses. And what we're going to do is I want to run this many, many, many times. So what I'm going to do here is if I scroll down a little bit, I'm going to go enumerate through all of those messages, right? And go do some work. So what are we going to do? So this is, I'm going to so I'm making it easier to work with some of these objects. I'm deserializing stuff into a message object. That is something that you see over here, just what a reference is. I'm taking the JSON response and I'm deserializing it into a strongly typed object using JSON.NET to make my life a little bit easier. So what I'm doing here is I'm going to walk through all those items that I got back in those different messages. And now what I'm going to do is I'm going to go grab each one, some details about each one of those emails. All right. So I've gotten a list of the top 100 emails in my mailbox. And now we're going to go through and create a bunch of tasks. The same way you saw me do this in the previous demo. So I'm going to go create a request. So I'm going to call a method here called get the message detail. And I'm going to write out the results. So you see I'm retrieving a message, go get it, and then write out the results. So what does get message detail do? Well, I'm using my HTTP client and I'm passing in the ID of the email message. We'll look at that in just a second. What that is then doing is that's coming over here and that's creating an instance of all, it's creating that big collection of all those requests, of 100 requests, and then it's going to go run all those requests simultaneously. And it's going to tell me how long that actually took as well. I'm using a stopwatch object to do that. So what is it actually going to do? Well, if I come down here a little bit farther, let's look at our get message detail. What is it doing? What get message detail is it's going to go create a request for that specific message using the Microsoft Graph API. So I'm going to go create the request that you see here, and I'm going to go create the request, and then I'm going to go write out what the response code was. If the response was successful, well, then I've got the message detail. I'm in good shape. But if the message was not successful, if instead I got a response of too many requests, which means that my request is being throttled, right, then so here what I'm going to do first is I'm going to set up a default delay. So you can see here that the get message detail has a parameter I can pass in of a default delay. And I'm setting it, if I don't pass it in, it's an optional parameter, and I'm setting the default value of it equal to a 2. So I'm saying we're going to retry after a delay of 2 seconds. Now that's the fallback that we're going to use in case I don't get a retry after value. And this is what we were saying in the slide, that in the slides just a second ago, that if you don't get a retry value back, you should at least have something that you're going to use, that you're going to fall back to. So here I'm going to check to see, does the response that we got back, does it include a retry after a header value? And if it does, so check to see if it does, and if it does, then and that value is greater than 0, then I'm going to set my retry after delay equal to the number of seconds that it's telling me that I should wait. Okay. Then what I'm going to do is I'm going to issue a sleep command. I'm going to sleep for that many seconds. So again, the sleep is a number of milliseconds. So in this case here, if it's default, I'll say 2 seconds times 1,000. So 2 times 1,000 milliseconds is 2 seconds. And then I'm going to make the exact same call a second time. Again, you should probably be a little bit more careful with this, to where you're checking to see if the same request is being made over and over and over, and I don't have a retry after being sent back to me, then I probably want to make this 2 seconds kind of be something a little bit more exponential. Like I maybe want to double it and then double it again, so that I'm not always waiting just 2 seconds. Maybe I need to add it to be 4 seconds or 8 seconds. That's something that's pretty easy to implement on your own, that you can figure that out. Okay, so you can see here, what we're doing here is we're simply going to wait for the request to where we can still issue it. So we want all of our requests to succeed. Unlike the previous demo, where only 34% succeeded, I want 100% to succeed. And the way I'm going to do that is that if any requests are throttled, then I'm going to wait for however long the Microsoft Graph tells me to wait, or it's going to be 2 seconds before I reissue that request. And so it may take longer for this whole process to run, but it will succeed. So let's go see this run. So I'm going to come over to my console, and I'll do a .NET build followed by a .NET run. So I'll paste in my username, and let me grab my password and paste that in. Now, what it's going to do is it's going through and getting a list of all of my email address, or the top 100 email addresses in my mailbox, and then it's going to create requests for each one of those to go fetch all of those emails and the details for those emails. And then it's going to submit all 100 of those requests at the same time, which is going to trigger some throttling responses, but we want to retry those requests to get throttled again to get the request, make sure the request succeeds. This is going to take a minute to run because we're going to get a lot of throttling requests. So through the magic of video editing, I'm going to skip ahead in time and just show you the final result. Okay, here we can see that all of our requests have finished. Now what I need to do is I need to go back and find, we see lots of these are okay requests, but there's got to be some that have actually failed because we should have overloaded it. So let's scroll back a bit. I'm sure we're going to find at least a couple that had, there we go, there's some throttle requests. So you can see here that we got a status code back for some stuff. And so we said, so the Microsoft Graph was telling us only a retry after it was giving us of just 1 second. We didn't have to use our default of 2 seconds because apparently 1 second was specified. So that's good. So we can see that we had too many requests come in. We waited for a second and submitted it again. And that time, the next time it ran just fine. And we got our email message back. So we can see that only happened a couple times, which is good, that we didn't overload the application. You can see that it's the synchronization of some stuff kind of got jumbled a bit. All right, so with this, you saw how to create a mitigation strategy for dealing with throttled responses, but that was using the HTTP client, and if you had to do it yourself. Let's see what happens or what's required for doing it if I wanted to use the Microsoft Graph. So let's come over to our second sample, and this is doing almost the exact same thing that we did previously, except I'm going to show you the difference that we have in this project. So here, again, we're getting the username and password, but I'm going through and getting the graph authenticated client. I'm not getting an HTTP client. And notice the difference is that I'm using the graph SDK. So in this case, go get all the email messages. So I'm using the same kind of a query we did before, except I'm just using the .NET SDK Fluent API. And then if I scroll down in my message detail, I want you to notice how simple this is. Remember the one that we had for let's go through and put these side by side so you can see a difference. So remember the message detail that we had for the HTTP client had a whole bunch of logic on how to go through and deal with 429s and if it was an OK or an OK response or a 429 response. What's neat about this is that the .NET SDK for Microsoft Graph already has all that retry logic built into it. So all I have to do is just say, go get that message. It gets it asynchronously and gives me the result. If it gets a throttle response, it uses that retry after header value, or it uses a default value to wait before resubmitting the request, and it will do it a certain amount of times. So you can see here that this one line of code is greatly simplifying how this works. And you can also see why we're using an HTTP client to demonstrate a strategy that you can employ, because if you didn't have access to one of the Microsoft Graph SDKs that has this retry ability built into it, it's nice to see how to do it if you had to do it manually. So let's see this in action. So we got to go back up to part 2 of this demo using the Graph client. Let's do a .NET build followed by a .NET run. We will have to log in again, so I'll log in using my username and my password. And here we can see it's going through the same process. And again, through the magic of video editing, we're going to let I'm going to go ahead and let this process complete, and we'll jump ahead to the finished result. So here we can see everything has completed. And unfortunately, I can't show you as easy, how often things were throttled versus how often things were not throttled, because the Microsoft Graph takes care of all that stuff for us inside of the SDK. So I can't really detect when things were throttled or not. But that's kind of a good thing too, because I don't have to deal with that logic in my application. I can just focus on the business logic and let the throttling and strategy be taken care of for me by the Microsoft Graph. And so in this demo, you saw how we could take advantage and implement a good throttling strategy inside of our applications. In this section, we're going to learn how Delta Query, also known as track changes, can be used to help avoid Microsoft Graph requests from being throttled. We're going to first look at avoiding polling Microsoft Graph for changes and then introduce Delta Query. And then we're going to see and talk about how we can use both Delta Query and track changes and change notifications to create a very robust application and process. Now, one very common scenario that custom applications implement is polling Microsoft Graph on scheduled intervals. Typically, this strategy is used to keep the application's local data store in sync with data exposed in Microsoft Graph. However, polling Microsoft Graph for changes usually requires multiple GET requests for a lot of data to be submitted in succession, a scenario that commonly triggers requests to be throttled. Now, one way you can mitigate throttling when polling Microsoft Graph for large data sets is to use the Delta Query feature of Microsoft Graph. Delta Query, also known as track changes, allows developers to request only data that has been added, updated, or deleted since the last request. Now, this pattern will allow the application to reduce the amount of data requested by the application, which will reduce the cost of the application and the request, and therefore likely limit the chances of the request from being throttled. Delta Query works using the concept of a state token. An application will issue initial request to Microsoft Graph the same way it normally does, except it will include the delta link function in the request. Microsoft Graph will respond with the requested data as normal, except the last page of data will include an extra property, delta link. This contains the endpoint with the state token of the Delta Query. Now, to request changes that have happened since the resulting data set from the time of the previous query was submitted, the application uses the endpoint from the previous request delta link endpoint. This tells Microsoft Graph to execute the same query, but only include the items that have changed since the previous request, as indicated using the state token that is included in the delta link property. The last page of results in this second request will include a new delta link property that you can store to use in the next request, and so on. Delta Query is supported by most Microsoft Graph resources, including directory roles, drive items, events in the primary calendar view, groups, mail folders, messages in a folder, personal contact folders in a folder, and users. Delta Query, when combined with another feature of Microsoft Graph, can be used to significantly reduce the number of requests to the Microsoft Graph. Change notifications are another feature of Microsoft Graph, which enables an application to be notified when changes occur to specific data. An application can subscribe to be notified when a specific resource changes, such as the users. When a user is added, updated, or deleted, the application is notified something changed in the user's endpoint by Microsoft Graph via an HTTP post. The application can then use Delta Query to request all the changes since the last time it made the request. Using this strategy, applications can nearly eliminate the need to frequently poll Microsoft Graph and process those changes to keep a local data store in sync. This greatly reduces the chances for their requests to be throttled. To ensure no changes are missed, it is recommended to schedule at least one long interval Delta Query request and not rely entirely on the subscription notifications to request changes from the Microsoft Graph. This will address all change data that can be processed by the application in case a change notification happened to be missed. In this final demo, we're going to use the existing .NET Core console application that we had created and the Azure AD application that we created to demonstrate how to work with Delta Query and how to use Delta Query. Now, the way this application is going to work, and we'll walk through the code in just a bit, is that it's going to request all of the users from our user collection for our tenant. And then once it does that, it's going to go to sleep and keep asking for all of the users over and over and over. But it's going to do that by saying, only give me the new users that have shown up since the last time that I issued the request. And it's going to do that using the Delta Query option. Now, in order to do that, we need to go modify our Azure AD application, and we need to go grant it an additional permission because we want to be able to look at all users. So I'm going to go add in another permission here. This permission is going to be a Microsoft Graph delegated permission, and we're going to use the user.read.all to go grab all users and in my organization. So I'll save that. And again, to simplify things, we're just going to go ahead and grant the permission to it. So we don't have to focus on the consent stuff aspect to this. Okay, so let's go take a look at the code for this. So what I've done is I've already gone ahead and I've updated the application to use the same credentials for this app. And now if I come down here to the program, let's look and see what this application is going to do. So what it's going to do is, notice that I have a global object that I've defined called Delta Link and a global object for the previous page. So what this does is it's going to come over here and it's going to grab all the users in the tenant. So I'm going to run check for updates the very first time. And then once that runs the first time, this check for updates is going to go write out all the users. So here what you can see is check for updates is going to go log the current user in. It's going to go get an authenticated graph client, go get all the users using the previous Delta link, which by default is going to be null. And then once it gets all those users, it'll write those users out to the console. It will keep doing that if it gets multiple pages in the response. So by default, only a certain number of users are going to be returned in each response. So if my request had, say, 1,000 users in my organization and I only get 100 per page, then I'm going to get one response that'll have a next link property. And so I need to go page through all of those next links until I get to the very end. I want to display all the users and then get to the very end. Once I get to the very end, I want to keep track of the delta link. So here I write out all the users in the first page. Is there another page? Yes, there is. Well, then go get that page and write those users out and keep going until the next page is equal to null, and then stop. And then what I'm going to do is I'm going to create an instance of a delta link. And what I'm going to look at the response that came back, look at the additional data on it, and I'm going to try to get a value of a delta link. And if I got it, then I'm going to go ahead and save it right here into this object. And then I'm setting it equal to my global object that I have. Now, once that happens, after that check for updates runs and gets all those users, that is when I'm going to create a break line. And then I'm just going to keep looping. And I'm going to keep looping until the application is terminated. So what I do is I'm going to say, I'm going to go to sleep for 10 seconds. So I'll go to sleep for 10 seconds, and then I'm going to issue the request again. And then I'm going to issue it again and again and again. So what I want to do is when I see this application run, it should run the first time. It should show me all my users and write them out. And then it should go to sleep and just keep running for the next, well, forever until I actually stop it. So all right, so let's go see this run. So I'm going to come over here to my application and do a .NET build followed by a .NET run. And I'll first pass in the username and the password. And it's going to go fetch all the users in my tenant and now go to sleep. So we've only got a few users in our tenant. So let's go over, we'll see it run again after 10 seconds, and it should show no new users because it's using Delta Query. Sure enough, no new users. Okay, so while that's running, let's go over to the browser and let's go into our Azure Active Directory and let's create a brand new user in our tenant. So I'll create a new user and we'll set their name to John Doe. So their name will be John Doe. And we'll just go ahead and create the user. There we go, successfully created. So let's come back over to the console and let's see, the next time it runs, it should pick up our new user. Oh, ran too quick on that one, so it didn't pick up the change on that one. So we'll let it run again. And there we go. Now we can see that it picked up the user of John Doe. So you see that it picked up just that change. Even though we had more users in there, it wasn't grabbing all of them. It just grabbed the ones that had changed since the last time it ran. And again, this is all happening because we've told it when we issue our request for all of our users, when it says get users, this is the one line that we didn't look at. I said that when we go get all of our users, I'm using the graph client and I'm including a delta request in the query, right? So I'm including a delta request in the query. And what that's doing is that's saying I always want to get only the things that have changed since the last time I ran this query. You can see here that if I did not have a previous page here, what I'm doing is I'm going through, walking through all the pages, and I'm using the previous delta query that I used in the last request. So again, the delta query, the delta link, that is the thing that we're storing with every time we finish a request. So in this demo, you saw how we could use a delta query to minimize polling for our application, although our demo application is polling, but it's showing us how we can only get the results of what items have been added or updated or deleted since the last time we ran the request. You could combine this with the change notifications capability that Microsoft Graph has, to where we could be subscribed to notifications to let us know when a user was updated or changed. It would notify us that a change happened, which would trigger us to go run our delta query to say, give me all the changes since the last time we ran, and it would just give me that one single user. So therefore, I wouldn't have to poll like I'm showing you right here. But the demo really wanted you to focus on seeing how to go about using and creating the delta query. Thank you very much for watching this module, and I hope you learned a lot about throttling with Microsoft Graph, how to identify it, how to avoid it, and then how to mitigate it with different strategies. Thank you very much, and I hope you enjoy future modules.